Good day, students. Today we're going to look at Unit 6, Integration and the Fundamental Theorem of Calculus. Hope you guys are doing well, and I hope you guys are still taking advantage of this flipped model that we're looking at, where you're watching these videos and doing problems before you come to class. As always, the PowerPoint that I'm doing here is available on Google Classroom. Okay, so I'm just going to do some examples that I think are pertinent to this particular subject. So the first thing I'm going to talk about is approximation using Riemann sums. So here we have a pool that has a filter that pumps water through it. The rate is given here, so as you can see here in the table, at some various times they're giving you the rate at which the water is flowing through. So at time t equals 1, the rate is 18 gallons per minute. And there's not really a question given here, so I'm just going to do this myself. So what if the AP exam says, okay, estimate the total number of gallons of water that flowed through the filter, let's say from time zero to time 10. So you're asked to estimate that. Now, we can't find it exactly because we're not given the function. We're just given some discrete pieces of information. So what we're going to do is we're going to do right Riemann sums. We could have done left, but in this case, I'm just going to say we're going to do right Riemann sums. So I'm just going to write right Riemann sums so we can get our estimate. So that means we're going to measure on the right. So we have 1, 2, 3 rectangles that we're going to do. And remember, since we're measuring on the right, we need to take the right-hand side of each of those rectangles for their height. And the area of a rectangle is base times height. So to find this amount of water, we're going to take this first width. The first width is 1 times the height on the right, which is 18, plus the second width, which is going to be 6 minus 1, which I think is 5, times the height on the right, which would be 24, plus the last width, which is going to be 4, times the height, which is going to be 17. We're going to add all of these together, and I think we get an answer of 206 gallons. If we were to do a left Riemann sum, then we would obviously measure on the left, etc. And again, this is just an estimate. Okay, this isn't the exact value. Our next example is going to involve the fundamental theorem of calculus, probably the most important theorem in calculus, thus it's called the fundamental. And basically it allows us to evaluate integrals, definite integrals. From this case a to b, we find the antiderivative of little f, we'll call that big F, and we simply evaluate that at b minus the evaluation of the antiderivative at a. So for example, if we wanted to find this definite integral, we would find that the antiderivative here, f, is going to be x to the 4th over 4, and then we would simply evaluate that from 0 to 5, and that's going to give us 625 over 4. So this is a quick way of evaluating definite integrals. I have another example here. I'm going to go ahead and skip this second example. See if I can erase some of this here so we can see the second example. You're given a definite integral on the right, and then you're given an expression on a definite integral on the left and an expression on the right, and you're supposed to find f of a, which is just a simple equation. The other thing that FTC allows us to do is to calculate the area under a curve. So if I want to find the area under this curve from, let's say, 0 to 2, that would be this area here all the way up to 2. So if I wanted to find this area, and I'm not talking about an estimate right now, if I wanted to find that exact area, I could do that using the fundamental theorem of calculus. Here's my function. Oops, I want to be on a pen. There's my function. Let me go ahead and erase that now that I've covered up part of it. And all I need to do is I need to integrate it on that interval. So that area is going to be the integral from 0 to 2 of 2x squared minus 3x plus 2 dx. And I'll let you guys calculate what that area is. Maybe this would be a good opportunity for you to practice using your calculator. Obviously, this one would be easy to do by hand, but if you've got your calculator, maybe you can type that in and see what that answer is. Here's an example of an AP problem. No calculator allowed. Now, obviously, this isn't going to be, there's no way that I don't think they'll be able to restrict this on the AP exam, but this is kind of the things you should expect on the exam, is they'll give you some things, and instead of coming right out and saying, hey, here's the fundamental theorem of calculus, you've got to kind of figure that out. So they're telling us that the graph is f prime, and then they're basically asking you to find f of 2, given that f of 0 is 8. So you're going to have to use the fundamental theorem of calculus here. In other words, what you're going to want to do is you're going to want to write something like, I'll put a question mark here and a question mark here of f prime dx, and that's going to be equal to, I'm going to call it f of b minus f of a. I will let you figure that out. You will have to use this initial condition, and I will tell you that the answer here is 13. There are actually two parts to the fundamental theorem of calculus. The second part involves finding the derivative of the integral. So here we're writing a function as an integral, and it basically turns out that the derivative of this integral, they undo each other. The only thing we got to be careful is if for some reason this x value here isn't just x, the derivative of x is just 1. So if I gave you this, and let's say this was 3, and this was just, let's say, x squared, then the answer would just be x squared. But here, since it's x to the third, the answer is going to be sine, and then you plug in the x to the third, which is what you would guess, but then you have to apply the chain rule here, so you'd have to multiply this by 3x squared. So this would be the derivative of that integral. Again, guys, this is all review, so I'm kind of moving through this quickly. Substitution method, u sub. So here you want to figure out what u is going to be. And what you want to try to do is you want this, the derivative of u, to be something like this. Well, the derivative of x squared plus 2 is 2x dx. So we're close. We got the x, but we got the 2, and you probably remember we go ahead and divide that 2 over, and we get 1/2 du equals x dx. The other thing I wanted to remind you is here, though, is we can actually go ahead and change these guys as well. So we can say that 3 is going to change to, well, now remember, this is in terms of x, so we want to make it in terms of u. So this is how we do that. So if you plug 3 in for x, you'll get 3 squared plus 1 is 10. So 3 is actually going to be 10 on our new equation, or our new integral. And then 4, again, we use the same rule, is going to be 4 squared plus 1. So I think that's going to be, what, 17? And we can use all of this information to write our new integral as follows. The integral of 4, oops, not 4, we want to use these guys here. From 10, that's not good. Erase. Get rid of that. Try that again. Oops. Okay, 10 to 17. Now don't forget about this 1/2 here. So we'll put the 1/2. Put the 1/2 here on the front. And now instead of u or x quantity x squared plus 1, we are simply going to write in our u. And remember, u here is actually to the third du. And now you can go ahead and figure out what that answer is. I think I've done that one already for you. I'm not going to go through all the details here, but it turns out to be 9,190 and 1/8. Again, you can check that with the calculator. That's a 0 there. Okay. So that's a U sub. Okay, so now this next example is only for Calc BC, and I know we're getting to that 10-minute mark. So this is Calc BC, Calc AB students, you can disregard this. So this is integration by parts. So here what we're trying to do is we're going to try to convert this into uv minus the integral of v du. So we want to try to figure out what substitutions to make here. And so we use liate. And so in this case, we're going to let u be the x term, and then dv is going to be the e to the x dx. And of course, then du is just going to be dx. And v, what would be the integral of e to the x dx? Well, that'd be e to the x. So now we can plug all of that information into this formula, and we're going to have x e to the x minus the integral, and now we're going to do v du. So v we said was e to the x, and then du is dx, and then we go ahead and finish this out. It's going to be x e to the x minus e to the x, and then don't forget your constant of integration plus c. So that's integration by parts. I know that's one of the easiest examples, but I want to just refresh your memory on that. Last example is improper integration. And I'd like you to think about, why do we need to do improper integration here? Well, the problem is, the reason we need to do improper integration here is this function is, and when I say this function, I'll call it f of x equals 1 over the cubic root of x, is not defined at 0. That's a problem. It's not defined at 0. If you put 0 in there for this function, you will get 1 over 0, which is not defined. That's why you have to use improper integration. So to do this problem, we're going to simply make it a limit as b goes to 0 plus, and since we're going from 0 to 1, I'm going to 0 plus. We can't go to 0 of the integral of b to 1 of dx over the third root of x. And now we're going to evaluate it this way. And so we find the antiderivative, and I'm going to kind of skip a step here just to kind of make this go a little bit faster. When you find the antiderivative here, you're going to get 3 halves x to the 2/3. And we've got to evaluate that from b to 1. So then we're going to get 3 halves, and then we're going to have to evaluate this x to the 2/3 from b to 1, and you, in essence, you're going to end up with an answer of 3 halves. But this would be the notation that you would use to do that. So we're at 13.5 minutes. I think that is the end of the presentation. That is where we'll stop it then. Hope you guys have a great day. Please get working on those problems.